In the vast darkness beyond Neptune's orbit, something ancient stirs. The interstellar comet 3I Atlas, a visitor from another star system entirely, continues its lonely journey through our solar neighborhood. This wanderer carries within its frozen heart the chemical fingerprints of stellar processes that occurred long before our sun ignited. The nucleus, perhaps 2 kilometers across, holds secrets from a stellar nursery that existed when our own solar system was nothing more than a collapsing cloud of gas and dust. As it drifts closer to our star, the comet's surface begins to respond to solar radiation with the patience of geological time. The warming happens gradually, almost imperceptibly, like the first breath of spring touching winter ice. Solar photons, having traveled 93 million miles from the sun's surface, finally encounter this ancient ice for the first time in perhaps millions of years. The interaction is gentle, persistent, inevitable. Water ice sublimates directly into vapor without melting, creating a thin atmosphere around the comet's nucleus. This coma expands slowly, methodically, like morning mist rising from a quiet lake at dawn. The process follows the inverse square law as distance to the sun decreases. Solar heating increases exponentially. At 5 astronomical units from our star, the comet receives 25 times more energy than it did at the orbit of Pluto. Yet even this dramatic increase unfolds with cosmic slowness. Carbon monoxide and carbon dioxide join the water vapor in this ethereal dance, released from depths where they have waited in crystalline patience. These molecules, frozen solid at temperatures approaching absolute zero, now taste sunlight for the first time since their parent star died billions of years ago. Each sublimating ice crystal carries isotopic ratios that speak of stellar nucleosynthesis in alien suns, of supernovae that scattered heavy elements across the galaxy before our solar system even existed. The comet's rotation period, measured at approximately 16 hours, creates subtle variations in the sublimation rate. As different regions of the nucleus face the sun, jets of vapor emerge from specific locations on the surface. These jets are not random. They follow the comet's topography, emerging from depressions and valleys where volatile materials have accumulated over cosmic time. The resulting coma develops an asymmetric structure, slightly elongated in the direction opposite the sun. Scientists estimate that 3I Atlas originated in the Oort cloud of another star system, perhaps ejected during a close stellar encounter eons ago. The mathematics of such events are well understood when 2 stars pass within a few light years of each other. Their gravitational fields can disturb the outermost comets in each system's Oort cloud. Some comets fall inward toward their parent star, while others are flung outward into interstellar space at velocities exceeding the escape velocity of their birth system. The precise mechanics of 3I Atlas's arrival in our solar system remain beautifully uncertain. Did a passing red dwarf star, perhaps Proxima Centauri during an earlier epoch, disturb its original orbit through gravitational perturbation? Was it nudged by the gravitational influence of a massive planet orbiting its parent star, a world we cannot detect across the light years? Or did the death throes of its parent star itself provide the initial impulse that sent this frozen wanderer into the darkness between stars? These questions linger in the astronomical literature like unsolved poems, mathematical elegance without final answers. The comet's trajectory through our solar system follows a hyperbolic path, indicating its interstellar origin with mathematical certainty. Its orbital eccentricity exceeds unity, meaning it will never return once it departs. This is a one-time encounter, a cosmic handshake between our sun and a messenger from distant stellar shores. The gravitational influence of Jupiter and Saturn will slightly modify its path, adding our solar system's signature to its trajectory as it continues toward interstellar space. Spectroscopic analysis reveals water vapor, carbon monoxide, and traces of organic compounds in the expanding coma. These measurements, taken by ground-based telescopes and space-based observatories, provide the first chemical census of material from another stellar system. The deuterium to hydrogen ratio in the water vapor differs slightly from that found in Earth's oceans, confirming the comet's foreign origin. Each photon of reflected sunlight carries information about molecular bonds formed in stellar environments unlike our own. Only took 4.5 billion years to reach us. Only traveled perhaps 25 trillion kilometers through the cosmic dark to arrive at this moment. Only needed to survive the absolute cold of interstellar space, the bombardment of cosmic rays, and the gravitational perturbations of passing stars to deliver its quiet message to our instruments. The probability of such an encounter seems impossibly small, yet here the ancient wanderer drifts, patient as geology, inevitable as mathematics. The comet bears no awareness of the electromagnetic drama it is about to initiate, no knowledge of the planet ahead, whose magnetic field will soon taste the essence of distant stellar winds. It simply exists, following the gravitational choreography of celestial mechanics, transforming slowly from pristine ice to expanding gas as our star's energy penetrates layers that have remained frozen since the youth of the galaxy. In its gradual awakening, 3I Atlas prepares to participate in an electromagnetic conversation with Earth's magnetosphere, a dialogue between worlds separated by both space and deep time. The solar wind begins its journey in the sun's corona, where temperatures reach 2 million degrees Celsius, and the plasma becomes so energized that our star cannot contain it. Protons and electrons, liberated from their atomic bonds by extreme heat, stream outward at velocities approaching 400 kilometers per second. This invisible river of charged particles carries with it the magnetic field lines of the sun itself, stretching and distorting them into vast spirals that extend far beyond the orbit of Pluto. At the distance of Earth's orbit, the solar wind maintains a density of approximately 5 particles per cubic centimeter, a vacuum more complete than anything achievable in terrestrial laboratories, yet dense enough to carry electromagnetic influence across the solar system. These particles, mostly hydrogen nuclei stripped of their electrons, have traveled for 4 days from the sun's surface before reaching our planet's neighborhood. Each proton carries kinetic energy equivalent to its motion through space, while electrons dance in complex helical patterns around the magnetic field lines. The wind structure reveals itself in layers and variations, fast streams, originating from coronal holes where the sun's magnetic field opens to space, race outward at speeds exceeding 800 kilometers per second. Slow streams, emerging from the sun's equatorial regions, maintain more sedate velocities around 300 kilometers per second. When fast streams overtake slow streams, they create compression region zones of enhanced density and magnetic field strength that sweep through the solar system like invisible waves. Embedded within this flow are the remnants of solar storms, coronal mass ejections that erupted from the sun's surface days or weeks earlier. These magnetic clouds carry field orientations that may oppose Earth's magnetic field, setting the stage for powerful geomagnetic storms when they arrive. The interplanetary magnetic field, carried outward by the solar wind, rotates with the sun's 27-day period, creating a vast spiral pattern known as the Parker spiral after the physicist who first described its geometry. The solar wind's magnetic field strength at Earth's orbital distance averages about 5 nanotesla, roughly 10,000 times weaker than a typical refrigerator magnet, yet sufficient to carry electromagnetic information across planetary distances. This field connects every planet in the solar system to the Sun's magnetic influence, creating what space physicists call the heliosphere, a vast bubble of solar influence extending perhaps 100 astronomical units into interstellar space. Between Mercury and Mars, the solar wind encounters no significant obstacles. Venus, lacking a global magnetic field, offers little resistance to the solar wind's advance. Mars, with only weak crustal magnetic fields remaining from its ancient dynamo, presents minimal deflection. Earth stands unique among the inner planets in possessing a strong, active magnetic field capable of creating a substantial impediment to the solar wind's progress. Scientists have wondered for decades about the precise mechanisms that accelerate the corona to such extreme velocities. The solar wind's existence was predicted theoretically by Eugene Parker in 1958, but the detailed physics of coronal heating and wind acceleration remain areas of active research. Magnetic reconnection events, wave heating, and turbulent dissipation all contribute to the process. Yet no single mechanism fully explains the observed temperatures and velocities. Only took the Sun 4 billion years to perfect this stellar exhalation. Only required the gravitational collapse of a primordial gas cloud, nuclear ignition, and billions of years of magnetic dynamo action to establish this constant outflow. Only needed to convert 4 million tons of matter into energy every second to maintain the pressure gradients that drive the solar wind's eternal journey outward through space. As 3I Atlas approaches the inner solar system, it encounters this invisible ocean of charged particles for the first time in its interstellar wandering. The comet's expanding coma, now stretching thousands of kilometers around its nucleus, begins to interact with the solar wind's magnetic field lines. Water molecules, dissociated by solar ultraviolet radiation, create hydrogen and oxygen ions that become entrained in the wind's flow. The interaction starts subtly. Individual molecules sublimating from the comet's surface become ionized by solar extreme ultraviolet radiation, losing electrons and acquiring positive charge. These newly created ions, still moving with the comet's orbital velocity, encounter the solar wind's magnetic field. The Lorentz force, acting on charged particles in motion through magnetic fields, begins to deflect these ions away from their original trajectories. A bow wave begins to form upstream of the comet as the solar wind encounters the expanding cloud of neutral gas and newly formed ions. This is not yet the dramatic bow shock that forms around planets with strong magnetic fields, but rather a gentler disturbance, a subtle modification of the wind's flow pattern as it accommodates the comet's presence. The solar wind, accustomed to traveling unimpeded through interplanetary space, must now navigate around an expanding obstacle of gas and dust. The comet's tail begins to take shape. Not yet the spectacular appendage visible in telescope images, but rather the first stirrings of plasma acceleration away from the nucleus. Ions formed in the inner coma experience the full force of the solar wind's electromagnetic field, accelerating them to speeds matching the wind itself. This creates a faint plasma tail extending opposite the sun's direction. Invisible to human eyes but detectable by sensitive spectrographs that can measure the Doppler shift of ion emission lines. The solar wind carries these comet ions away into the outer solar system, incorporating alien chemistry into the heliospheric plasma. Material that originated in another star system now mixes with the sun's own stellar wind, creating a dilute but detectable signature of interstellar matter distributed throughout our local cosmic environment. The comet has begun to exhale its ancient substance into the solar wind's embrace, preparing for the more dramatic electromagnetic encounters that await as it continues its approach toward the inner planets. Deep beneath Earth's surface, 3,000 kilometers down, where pressures exceed those found at the bottom of the deepest ocean trenches. Liquid iron churns in the planet's outer core. This metallic ocean, heated to temperatures rivaling the Sun's surface, moves in vast convective currents driven by the gradual cooling of Earth's interior and the crystallization of the inner core. As this conducting fluid flows through the weak magnetic field that permeates space, it generates electrical currents that amplify and sustain Earth's magnetic field through a process known as the geodynamo. The magnetic field lines emerge from the southern magnetic pole, arch high above the planet's surface, and converge again at the northern magnetic pole, creating a vast dipolar structure that extends tens of thousands of kilometers into space. This magnetosphere, the region where Earth's magnetic field dominates over the interplanetary magnetic field, forms an invisible shield around our planet, deflecting most of the solar wind's charged particles away from the atmosphere and surface below. The magnetosphere's shape reflects the constant pressure of the solar wind against its outer boundary. On the day side, facing the Sun, the magnetic field lines are compressed to a distance of approximately 10 Earth radii. On the night side, away from the solar wind's direct pressure, the field lines stretch into a long magneto-tail extending more than 100 Earth radii into space. This asymmetric structure creates a teardrop shape, like a cosmic windsock indicating the direction of the solar wind's flow. Within this magnetic cocoon, charged particles follow complex trajectories governed by the Lorentz force. Electrons and protons spiral along magnetic field lines, bouncing between the northern and southern hemispheres in motions that can take seconds to minutes to complete. Some particles become trapped in the Van Allen radiation belts, toroidal regions of enhanced particle density that encircle the Earth at altitudes between 1,000 and 60,000 kilometers. The magnetosphere's boundary layers reveal the complexity of space plasma physics. The magnetopores, the outermost boundary where solar wind pressure balances magnetic pressure, fluctuates continuously as variations in solar wind density and velocity alter the force balance. Inside this boundary lies the magnetosheath, a turbulent region where solar wind plasma has been decelerated and heated by its passage through the bow shock that forms upstream of the magnetosphere. Earth's magnetic field strength varies across the planet's surface, ranging from about 25 microtesla near the magnetic equator to 65 microtesla near the magnetic poles. This variation reflects the dipolar nature of the field and the 11-degree offset between the magnetic and geographic poles. The magnetic North Pole currently wanders across the Canadian Arctic at a rate of approximately 55 kilometers per year, following complex patterns driven by changes in the core's fluid motion. Scientists have traced the history of Earth's magnetic field through paleomagnetic studies of ancient rocks and sediments. The field has reversed its polarity hundreds of times throughout Earth's history, with the most recent reversal occurring approximately 780,000 years ago. During these reversals, which can take thousands of years to complete, the magnetic field strength drops to about 10% of its normal value, potentially allowing increased cosmic ray bombardment of the atmosphere. The geodynamo's precise mechanism remains one of Earth science's most challenging problems. Computer simulations of core convection require enormous computational resources and still cannot fully reproduce all observed features of the magnetic field. The interaction between thermal and compositional convection, the role of the inner core's growth, and the effects of precession and tidal forces all contribute to the dynamo's operation in ways that are not yet completely understood. Only took 4.5 billion years for Earth to develop this protective electromagnetic embrace. Only required the differentiation of heavy elements toward the center, the establishment of core convection, and the precise balance of thermal and rotational forces to create a self-sustaining magnetic dynamo. Only needed the fortuitous combination of a liquid outer core and a solid inner core to generate the complex field geometry that shields life from the harsh realities of space weather. The magnetosphere responds to external influences with the sensitivity of a vast electromagnetic instrument. Changes in solar wind pressure cause the magnetopores to move inward or outward, compressing or expanding the entire magnetic cavity. Variations in the interplanetary magnetic field orientation can trigger magnetic reconnection events at the magnetopores, allowing solar wind energy to penetrate deep into the magnetosphere and powering geomagnetic storms. During quiet periods, the magnetosphere maintains a relatively stable configuration, with well-defined current systems flowing along the magnetopores and within the magnetotail. The ring current, a westward flowing current of energetic particles encircling Earth at distances of 3 to 7 Earth radii, creates a small but measurable depression in the planet's surface magnetic field. This current intensifies during geomagnetic storms, causing the distinctive decrease in horizontal magnetic field strength that ground-based magnetometers record as the Storm Time Deist Index. The aurora borealis and aurora australis provide visible evidence of the magnetosphere's interaction with solar wind particles. When magnetic reconnection in the magnetotail accelerates particles earthward along magnetic field lines, these particles collide with atmospheric gases at altitudes between 100 and 400 kilometers. Oxygen atoms emit green light at 550.7 nanometers when excited by electron impact, while nitrogen molecules produce blue and red emissions that paint the polar skies in shifting curtains of color. As 3Y Atlas continues its approach toward the inner solar system, its expanding coma and developing plasma tail will soon encounter this vast magnetic structure surrounding Earth. The comet's ionized gases, already entrained in the solar wind's flow, carry electromagnetic signatures that will test the magnetosphere's response to foreign plasma chemistry. The ancient ice, now transformed into charged particles streaming away from the comet's nucleus, prepares to engage in an electromagnetic dialogue with Earth's protective magnetic embrace, a conversation between terrestrial geophysics and interstellar chemistry that will unfold across the vast scales of space plasma physics. As 3I Atlas draws closer to the Sun, crossing the orbital distance of Jupiter, the increasing intensity of solar radiation begins to transform the comet's tenuous coma into something far more dynamic. The process unfolds with glacial patience, yet each passing hour brings measurable changes to the comet's electromagnetic environment. Water molecules, liberated from the nucleus through sublimation, drift outward at velocities of several hundred meters per second, creating an expanding sphere of neutral gas that grows larger with each orbit around the Sun. Solar ultraviolet radiation, particularly the extreme ultraviolet photons with wavelengths shorter than 100 nanometers, carry sufficient energy to ionize these water molecules through photoionization. Each photon collision strips away an electron, transforming neutral H2O into positively charged H2O plus ions that immediately become subject to electromagnetic forces. The ionization rate increases dramatically as the comet approaches perihelion, with the cross-section for photoionization scaling inversely with the square of the distance to the Sun. The newly formed ions retain the orbital velocity of their parent molecules initially, but the Lorentz force, the fundamental electromagnetic force acting on charged particles in motion through magnetic fields, begins to accelerate them in directions perpendicular to both their velocity and the local magnetic field. This creates a complex choreography of particle motion as ions spiral around magnetic field lines carried outward by the solar wind, their trajectories becoming increasingly stretched and distorted. Electron impact ionization adds another layer of complexity to the process. High-energy electrons in the solar wind, with energies exceeding the ionization potential of water molecules, create additional ions through direct collision. This secondary ionization process becomes particularly important in regions where the solar wind's electron temperature is elevated, such as within magnetic clouds or compression regions swept up by fast solar wind streams. The comet's plasma tail begins to take definitive shape as these processes accelerate. Unlike the dust tail, which follows the comet's orbital path and curves gently away from the Sun due to radiation pressure on solid particles, the plasma tail extends almost directly away from the Sun, guided by the magnetic field lines embedded in the solar wind. This plasma tail can extend for millions of kilometers, though its density remains extraordinarily low, perhaps 1,000 ions per cubic centimeter, comparable to a good laboratory vacuum. The tail structure reveals itself in filamentary patterns visible to sensitive spectrographs that can detect the emission lines of ionized gases. Carbon monoxide ions emit strongly at wavelengths around 427 nanometers, while water group ions produce emissions across a broader spectrum. These spectral signatures provide astronomers with a remote sensing capability, allowing them to measure ion densities, temperatures, and velocities from ground-based observatories millions of kilometers away. Magnetic draping occurs as the solar wind's field lines encounter the expanding coma of neutral gas. The interplanetary magnetic field, unable to penetrate regions of high neutral density, becomes draped around the comet's nucleus like invisible cloth flowing around an obstacle. This creates a complex magnetic field geometry where field lines pile up on the upstream side of the coma and stretch into long, twisted configurations downstream. The plasma tail's brightness varies with solar wind conditions and the comet's gas production rate. During periods of enhanced solar wind density or velocity, the increased ion production and acceleration create more prominent tail structures. Conversely, when the interplanetary magnetic field orientation is unfavorable for efficient ion pickup, the tail may appear fainter or less well-defined in telescopic observations. Scientists have identified several distinct regions within the comet's plasma environment. The inner coma, extending perhaps 10,000 kilometers from the nucleus, contains mostly neutral molecules with a small fraction of newly formed ions. The outer coma, stretching to hundreds of thousands of kilometers, shows increasing ion fractions as photoionization and electron impact ionization transform the neutral gas. The plasma tail itself represents the final stage of this transformation, where ions have been fully accelerated to solar wind velocities. Only took solar radiation 8 minutes to travel from the Sun's surface to begin this transformation. Only needed photons with energies of 12.6 electron volts to strip electrons from water molecules and initiate the ionization cascade. Only required the precise electromagnetic choreography of solar wind magnetic fields to organize these scattered ions into the coherent structure of a plasma tail streaming across millions of kilometers of space. The comet's rotation, with its 16-hour period, creates temporal variations in the ion production rate as different regions of the nucleus face the Sun. Active areas, where subsurface ice lies close to the surface, produce jets of vapor that create dense regions within the coma. These jets, detected through high-resolution imaging and spectroscopy, show how the comet's topography and internal structure influence the development of its plasma environment. As the ions accelerate away from the nucleus, they carry with them isotopic signatures that reveal the comet's formation environment. The deuterium to hydrogen ratio in water vapor, measured through infrared spectroscopy, differs from that found in Earth's oceans, confirming the comet's origin in a stellar environment with different nucleosynthetic processes. Heavy water molecules, containing deuterium rather than ordinary hydrogen. Ionize at slightly different rates and follow subtly different trajectories in the plasma tail. The magnetic field embedded in the plasma tail develops its own dynamic structure. Magnetic reconnection events, where oppositely directed field lines merge and release magnetic energy, can create localized acceleration regions within the tail. These magnetic reconfigurations, occurring on timescales of minutes to hours, contribute to the complex, ever-changing structure of the comet's plasma environment as it continues its approach toward the inner solar system and its eventual encounter with Earth's magnetosphere. The magnetosphere's bow shock stands as Earth's first line of electromagnetic defense, a vast curved surface extending approximately 90,000 kilometers upstream from our planet, where the supersonic solar wind first encounters the obstacle of Earth's magnetic field. This invisible boundary exists in a state of constant motion, expanding and contracting in response to variations in solar wind pressure, like the surface of a soap bubble responding to changing air currents. The shock itself measures only a few hundred kilometers thick, yet within this narrow region, one of the most dramatic transformations in space, physics unfolds continuously. As 3I Atlas approaches the inner solar system, its expanding plasma tail carries ions that have been accelerated to velocities matching the solar wind itself. These foreign particles, bearing the chemical signatures of stellar processes that occurred in distant star systems, become embedded within the solar wind's flow as they stream past Earth's orbital distance. The solar wind, now enriched with this interstellar chemistry, encounters Earth's bow shock with slightly altered composition and electromagnetic properties. The shock formation occurs when the solar wind's supersonic flow, traveling at speeds exceeding the local sound speed in the plasma, meets the immovable obstacle of Earth's magnetic field. Unable to flow around this electromagnetic barrier as easily as it flows around planets lacking strong magnetic fields, the solar wind undergoes a violent deceleration. Kinetic energy converts to thermal energy, heating the plasma to temperatures exceeding 1 million degrees Celsius, while simultaneously slowing its bulk velocity from 400 kilometers per second to perhaps 100 kilometers per second. The shock's geometry follows the laws of magnetohydrodynamics, creating a paraboloid shape that extends far into the solar wind upstream of Earth. The nose of the shock, directly between Earth and the Sun, typically lies at a distance of 13 to 14 Earth radii, though this distance varies significantly with solar wind dynamic pressure. During periods of high solar wind density or velocity, the shock moves closer to Earth, compressing the entire magnetospheric system and intensifying the electromagnetic interactions within. Particle acceleration occurs naturally at the bow shock through a process known as diffusive shock acceleration. A small fraction of the incoming solar wind protons and electrons undergo multiple interactions with the shock front, bouncing back and forth across the boundary while gaining energy with each crossing. This mechanism can accelerate particles to energies hundreds of times greater than their initial thermal energies, creating a population of energetic particles that contributes to the radiation environment near Earth. The shock's magnetic field structure becomes highly complex as the interplanetary magnetic field encounters this boundary. Field lines become compressed and tangled, creating regions where the magnetic field strength can be 4 to 5 times greater than in the undisturbed solar wind. These compressed field regions store magnetic energy that can be released through magnetic reconnection events, contributing to the dynamic nature of the shock environment. When the plasma tail ions from 3I Atlas first encounter this bow shock, they experience the same violent deceleration and heating as the ambient solar wind particles. However, their different mass-to-charge ratios cause them to respond differently to the electromagnetic fields present at the shock. Heavy ions, such as those formed from carbon monoxide or carbon dioxide molecules, gyrate around magnetic field lines with larger radii than protons, creating distinct spatial distributions in the shocked plasma. The shock exhibits a phenomenon known as reformation, where the shock front periodically steepens and relaxes on timescales of a few minutes. This process reflects the complex interplay between incoming particles and the electromagnetic fields they generate, creating a dynamic boundary that constantly adjusts its structure to maintain the energy balance required for shock formation. High-resolution spacecraft measurements reveal that the shock front contains multiple layers and substructures that evolve continuously. Scientists have identified several types of bow shock depending on the angle between the incoming solar wind and the local magnetic field orientation. Quasi-perpendicular shocks, where the magnetic field lies nearly perpendicular to the shock normal, tend to be more stable and efficient at thermalizing the incoming plasma. Quasi-parallel shocks, where the field lines are more aligned with the shock normal, often exhibit turbulent foreshock regions extending far upstream where reflected particles create electromagnetic waves and instabilities. Only took the solar wind 4 days to travel from the Sun before encountering this electromagnetic barrier. Only needed the precise balance of magnetic pressure and plasma pressure to create a boundary capable of deflecting a supersonic flow of charged particles around an entire planet. Only required the complex physics of collisionless plasma shocks to transform the kinetic energy of stellar wind into the thermal energy that heats the magnetosheath to temperatures exceeding those found in stellar coronas. The foreshock region, extending upstream from the bow shock along magnetic field lines connected to the shock surface, becomes populated with particles reflected from the shock front. These reflected ions and electrons create electromagnetic waves that propagate back into the undisturbed solar wind, effectively announcing the presence of Earth's magnetic obstacle to incoming plasma streams. The wave activity in the foreshock can extend tens of thousands of kilometers upstream, creating a complex electromagnetic environment that modifies the solar wind properties before they reach the shock itself. As ions from 3I Atlas's plasma tail encounter these foreshock waves, they experience additional acceleration and scattering that modifies their trajectories before they reach the main shock front. The foreign chemistry of these interstellar particles adds new spectral signatures to the electromagnetic emissions generated in the foreshock region, creating subtle but detectable modifications to the radio and plasma wave environment that sensitive spacecraft instruments can measure. The bow shock's response to the presence of heavy ions from the comet's plasma tail remains subtle but measurable. The additional mass loading slightly reduces the shock's efficiency at thermalizing the incoming flow, while the different charge-to-mass ratios of the comet ions create distinct populations in the downstream magnetosheath region. These effects represent the first electromagnetic signatures of the comet's interaction with Earth's magnetospheric system, a gentle herald of the more complex plasma physics phenomena that will unfold as the interaction intensifies. In the space between the bow shock and the magnetopores, within the turbulent region known as the magnetosheath, magnetic field lines from Earth's magnetosphere and the interplanetary medium approach each other with the inevitability of opposing forces in cosmic tension. When these field lines carry opposite orientations, northward, Earth field, meeting southward, interplanetary field, or vice versa, the conditions become favorable for one of the most fundamental processes in space, plasma physics magnetic reconnection. The field lines, unable to maintain their separation when pressed together by the solar wind's relentless pressure, suddenly snap and reconfigure into new topological arrangements. The reconnection process occurs at the magnetopores, the boundary between Earth's magnetic domain and the solar wind's electromagnetic influence. This boundary, typically located 10 to 12 Earth radii from the planet's center on the day side, fluctuates continuously as solar wind pressure varies and magnetic field orientations change. When reconnection begins, it creates what plasma physicists call an X-line, a narrow region, perhaps only a few hundred kilometers wide, where the magnetic field topology undergoes rapid reorganization. Energy stored in the stressed magnetic field configuration releases explosively during reconnection events, converting magnetic energy into kinetic energy of charged particles. Electrons and ions accelerate away from the reconnection site at velocities that can exceed 1,000 kilometers per second, carrying enormous amounts of energy into both the magnetosphere and back toward the solar wind. The process resembles a cosmic capacitor discharging, releasing energy that has been slowly accumulated as the solar wind compresses Earth's magnetic field. As ions from 3I Atlas's plasma tail reach the magnetopores, they carry with them the magnetic field signature of the interplanetary medium in which they have been traveling. These foreign ions, with their distinct isotopic compositions and charge states, become participants in the reconnection process as the comet-modified solar wind encounters Earth's magnetic barrier. The heavy molecular ions H2O+, CO+, CO2+ behave differently from the simple protons and electrons that typically dominate solar wind composition. The reconnection process creates distinctive plasma jets that accelerate particles along the newly reconfigured magnetic field lines. These jets, observable through their characteristic signatures in particle and field measurements, transport energy and momentum across the magnetopores boundary. When reconnection occurs on the day-side magnetopores, it can inject solar wind plasma directly into the magnetosphere, while night-side reconnection in the magnetotail can expel magnetospheric plasma into the solar wind. The rate of magnetic reconnection depends critically on the orientation of the interplanetary magnetic field relative to Earth's dipolar field. When the interplanetary field points southward, anti-parallel to Earth's northward-pointing field at the day-side magnetopores, reconnection proceeds efficiently and can transfer significant amounts of solar wind energy into the magnetosphere. Northward interplanetary field orientations generally result in much weaker coupling between the solar wind and magnetosphere. Magnetic reconnection exhibits a phenomenon known as bursty reconnection, where the process alternates between periods of rapid energy release and relative quiescence. These bursts, lasting from seconds to minutes, reflect the complex feedback between the reconnection process and the surrounding plasma environment. The newly reconnected field lines can become loaded with plasma, reducing the efficiency of further reconnection until the field lines have been cleared by plasma transport processes. The presence of heavy ions from the comet's plasma tail subtly modifies the reconnection dynamics through their different mass-to-charge ratios. Heavy ions gyrate around magnetic field lines with larger radii than protons, creating distinct spatial scales in the reconnection region. This mass loading effect can reduce the reconnection rate while creating more complex particle acceleration patterns within the reconnection jets. Scientists have observed that the magnetic reconnection process creates its own electromagnetic signatures that propagate throughout the magnetosphere as Alfvén waves, low-frequency oscillations that travel along magnetic field lines at the Alfvén velocity. Typically, a few thousand kilometers per second in the magnetospheric environment. These waves can trigger responses in distant regions of the magnetosphere, coupling reconnection events at the magnetopores to phenomena in the radiation belts and ionosphere. Only took magnetic field lines microseconds to reconfigure once the reconnection process began. Only needed the precise alignment of opposing magnetic fields and the presence of sufficient plasma to mediate the electromagnetic interaction. Only required the conversion of magnetic stress energy, accumulated over hours of solar wind compression, into the kinetic energy of accelerated particles streaming away from the reconnection site at supersonic velocities. The dance of magnetic reconnection continues with rhythmic persistence as the orientation of the interplanetary magnetic field varies with the rotation of the Sun and the passage of solar wind structures. Each reconnection event transfers approximately 10^15 joules of energy from the solar wind to the magnetosphere, equivalent to the energy content of a moderate earthquake. Yet occurring in the rarefied plasma environment of near-Earth space, where such enormous energy transfers create barely perceptible disturbances in the terrestrial environment below. As 3U Atlas continues its orbital journey, the flux of heavy ions from its plasma tail provides a continuous supply of foreign chemistry to the reconnection process. These ions, once locked in crystalline ice structures formed in the cold depths of another stellar system, now participate in the electromagnetic choreography of Earth's magnetospheric boundary. Their presence adds new spectral lines to the electromagnetic emissions generated during reconnection, creating subtle but measurable signatures that space-based instruments can detect and analyze. The reconnected magnetic field lines, now carrying a mixture of terrestrial and interstellar plasma, begin their journey through the magnetosphere. Those that reconnect on the dayside magnetopores are swept over the polar regions toward the nightside magnetotail, where they may participate in additional reconnection events that eventually return them to the solar wind. This circulation pattern, driven by the continuous pressure of the solar wind and mediated